Okay, so now our diagonalization process is more going to be like, given some matrix looking like this, I want to find its secret, private, proper directions that are going to be the ones that are simply scaled by this matrix. Okay, I want to find the corresponding number and directions that are really defining this matrix once I find the good angle to view at it. Okay, so we start by saying, well, this is going to bear some nice names. Well, eigenvalue, it's corresponding to the 2 and -1 that we saw earlier. Eigenvector, they are going to be the directions, the privileged directions of my matrix, like the v1 and v2 vectors that we saw in that example. Eigenspace is going to be the linear space associated to an eigenvalue and the corresponding eigenvectors. And diagonalization, well, is of course what we are trying to do, diagonalize a matrix. Okay, so all these words, eigen, they come from, I think, German. It just means proper. In French, we use vecteur propre, valeur propre, sous-espace propre, et diagonalisation. Diagonalisation. Okay, so let's give a proper definition. An eigenvalue of A doesn't exist alone. In order to define an eigenvalue, so the usual letters that are used are going to be lambdas, well, but or mu's, or well, usually Greek letters, but it's just a number which can be real or it could be a complex number, even if you have a real matrix. Uh, so this number is an eigenvalue of A if there exists a non-zero vector V, okay, in Rn, such that A times V is equal to lambda times V. Okay, this is really what we tried to show in the previous example. V is going to be one of these favorite direction in Rn. So my matrix A is an n times n matrix. So that means that it takes a vector in Rn because I've got n columns and sends you a linear combination of those columns which have n components because I've got n rows. Okay, so my matrix A goes from Rn to Rn. And so lambda is an eigenvalue if I've got a non-zero eigenvector, if I've got something such that A times V is equal to lambda times V. Okay, so that's the definition. So in our previous example, we had V1 was an eigenvector associated to eigenvalue 2, because anything that, because V1 was just multiplied by 2 if you applied this transformation. And V2 was also an eigenvector associated to eigenvalue -1, because V2 would be sent to minus itself to its opposite if you applied the corresponding matrix. Okay, so eigenvalue, a real or complex value, and eigenvector, the vector that it corresponds to. So you see in the eigendirection, you really have something like just a scaling of your vector. The action of the matrix is just a scaling of the vector. All right, so we have met the eigenvalues and its associated eigenvectors, and you have a nice question here. Show that any vector collinear to V is also an eigenvector for the same eigenvalue lambda. Okay, so maybe I can let you think about this for 30 seconds, 1 minute. You just need to write it. Okay, so have you done that? Have you been able to see that? So let's see. Uh, so I've got V, my eigenvector associated to eigenvalue lambda, and I take some vector, let's call that W, which is collinear to V. So it just means that W is equal to some real number times V. So what is going to be the action of A on W, right? A times W is A times K times V. And by linearity, that's just going to be K times K is, I remind you, it's just a scalar value, a real value, A times V, but A times V is really lambda times V because V is an eigenvector associated to eigenvalue lambda, so K lambda V, and so the lambda I can put it before, that's commutativity of that's just real multiplication, K times V, and this is really lambda times W, okay? So if you've got one eigenvector, of course, anything that is going to be collinear to this eigenvector is going to be also an eigenvector corresponding to the same eigenvalue. Okay, so that's important to remember, and that's just will become, I guess, very natural when we get more acquainted to this. Okay, nice. Next comes a very nice definition. The spectrum of A is the set of all eigenvalues, and it's often denoted SP of A. Isn't that nice? Okay, so I've never really been able to find out who was the first person to employ this word for diagonalization, but for the set of all eigenvalues, but I think it's really nice because you see, let's look at this example. You started with a very full matrix, so something with a lot of non-zero and rational coefficients, and quite a complicated one. And then we could extract something very essential to that, just these diagonal values, these values on the diagonals, and that the set of these values is like the essential values of this matrix. So that's called the spectrum. Okay, so that's nice denomination. All right, so let's go a bit further. The main property that is going to help you find eigenvalues and eigenvector is this one. If V of lambda, V with the subscript lambda is an eigenvector associated to lambda, then that means that V lambda belongs to the null space of A minus lambda I. Okay, why? Very, very simply, comes from the definition. Let's work on the above definition. V is an eigenvector, so we called it V of lambda. Associated to eigenvalue lambda, it means this is what it means. Okay, in other words, what does it mean? Let's put that on the other side. A V lambda minus lambda V lambda is equal to 0. Do you see where I'm going to? The lambda times V lambda, lambda is a real, V lambda is an or n item. That's going to be also lambda times the identity of or n times V lambda equals to 0, which I can absolutely rewrite. A minus lambda I times V lambda is equal to 0. Okay, which of course I can directly translate as V lambda belongs to the null space of my matrix A minus lambda I. Okay, so what does it mean? It means that you are looking for eigenvalues, eigenvector, find the null space of A minus lambda I. Okay, and we will see how we find that. All right. Well, you can just write it, or we can, well, you will need to write it when you want to find eigenvectors, but we will see that it also leads to a very nice way to find eigenvalues. Okay, let's go on one more definition. The eigenspace associated to eigenvalue lambda is just the null space of A minus lambda I. Okay, and so that, of course, it's a vector space because we saw that the null space was a vector space. Please be sure you know why this is a vector space and be sure you know how to prove that in 30 seconds. Okay, so if you don't know, please ask that in the chat. Okay, all right. Next question is quite important. If 0 is in the spectrum of A, we never said that 0 should be excluded, but yes, indeed, 0 should be in the spectrum of, could be in the spectrum of A. That's a possibility. What exactly is the corresponding eigenspace? Well, obviously, you just have to substitute lambda by 0. So the corresponding eigenspace is just going to be, well, the null space of A, right? So conversely, we can say that 0 belongs to the spectrum of A, if and only if the null space of A is not reduced to 0. Okay, so maybe that's important enough so that we should write it as an additional property. 0 belongs to the spectrum of A. That means the null space of A is not reduced to only the 0 element. Probably it comes later in the document. I don't know, maybe, but that's anyway. That's a very important property that you have to be conscious of. All right.